more and more positive, and this is true in mice, rats, and humans. There's far more stories, like nitration of NGF is also involved in this, and it's being nitrated in astrocytes, and that's inducing death. So the summary is that I argue our CCS mouse is actually a humanized model of ALS, because every human that has this disease has CCS in 2 gene copies and 1 mutant. So we're just reestablishing the balance. The reviewers argue that it's not a model of ALS at all, and so forget it. I haven't talked about this, but actually there's a lot of good evidence that what's happening with the SOD mutations is they frustrate metal binding. What they do to the overall protein is they just disrupt it enough. Sometimes they stabilize the protein, but it's very clear it interferes with the proper insertion of metals. And so that's what the gain of function is. It's related to metal binding in some way. Then there's a huge amount of the protein, because it's overexpressed in the spinal cord, that doesn't have copper. That makes sense because copper import into the spinal cord is extremely slow. The turnover of copper in a mouse brain is over a year. It just doesn't get in, and it doesn't get released very often. And we need CCS to load copper into SOD. And if it's there in these mutant mice, it's sucking copper away from cytochrome C oxidase. That's creating the early death. And then if we give the copper ATSM, that's able to get copper into the brain and reload SOD, and also replete and activate the cytochrome C oxidase. But copper ATSM is doing more than just delivering copper. It works in many models of Parkinson's disease, which aren't due to a copper deficiency, and we're trying to understand some of that pathology. I want to take, running long, but I just want to show you, we've been playing with mass spec further. And we've invented a device that gets put in the mass spec and involves a light bulb filament and 2 magnets. And it holds electrons right in the path of ions. Because the problem I have is, can I actually localize where a metal is bound in a protein? The same's true if you want to measure phosphorylation. It's really tough to do by mass spec because the fragmentation methods knock off phosphate groups. And so what we've come up with is a method where, with this device, this is the hot filament, and these are the magnetic field lines from the magnets. And what happens is, if you put a voltage on, you can start to suck the electrons off the filament, but then they get parked out here and stuck, so they have very low energy. And that's perfect for binding to proteins at the peptide bond. So when proteins fall through, they, by the time they traverse the cell that's only a centimeter or 2 long, they become fragmented at one spot. And it's like creating a DNA sequencing gel that you can sequence proteins. And you can do it now in like 30 seconds. In principle, we can do it in 1/10 of a second. So this shows the copper zinc protein, and there's copper bound on one end of the protein and zinc's bound on the other. So in a case, if we can put an electron right here, we can actually separate the 2 sides. And then the electron binds to the peptide bond, it creates a break and separates into 2 pieces. And it's a quantum effect so that there's not energy being put in. Collision-induced dissociation involves hitting it with a baseball bat, and that knocks a lot of things out. Here it turns out the metals actually stay bound to the protein, and this was the shocking result. So we've isolated the protein, and you can actually purify it in one part of a mass spec and pass it on to the next part. And then when we turn on the electrons, you get what looks like this incredible amount of noise. But if you amplify it, probably you have to look over here, it turns out that each of those is a piece that's exactly predicted from its sequence. And the multiple spikes here, these are isotopes having different amounts of carbon-13. So these are 2 proteins, one that's missing copper, one that's missing zinc. And you can see in places where we can find copper bound at one site, but not, and zinc on the other protein. So the reason why we spent 10 years building these machines, is I can actually start to take SOD now and figure out, does it have copper in it, does it have zinc? Because you can't do it separately, and there's been no other method where you could begin to do this. So I don't know what the final answer will be, but we're having fun with it. So anyway, there are a lot of people that contributed to this, and I'll be happy to answer questions. Yes?